13 meters of diameter. And so if you're wishing to come by, please just let me know. So I thank Freddie and Antoine very much for inviting me to give this talk. I actually wanted the subject, which I'm just talking about ongoing work, and I wanted to talk about it with Freddie and Antoine some months ago, just after I got the email from Freddie and who invited me to give the talk here. So I said it's a good opportunity to talk about my work. So the first title, a little bit complicated. What I'm really talking about is ARC interaction. And for those who have been to my office, this is the painting, a poster of a painting which is hanging in my office. It's a painting from Gerhard Richter. He's probably the most selling or best selling painter, living painter, German painter. And it just means part of the ocean. And it shows, for me, it shows very well ocean-atmosphere interaction. So you have the ocean, you have the atmosphere. Both look turbulent and looks a little bit scary too. And so, well, this is, I like this painting very much. And this is another drawing of ARC interaction, which is a little bit more scientific. It comes from Woods Hole Institution of Oceanography, and it gives us an idea of what is really going on at the ocean-atmosphere interface. And today I will talk about only one process which is happening, and this is here the wind stress. So the wind imposing a stress on the ocean, because if there's wind blowing above the ocean, and if the ocean current and the wind's velocity are different, then there's some shear and there is some interaction. Of course, when both move at the same velocity, then there is no shear, but when they have different velocities, then there is a shear. So this will be the essential of my talk. And so I will just talk about a very, very simple model. It's a very idealized toy model, so it's kind of idealization type 1. So it's very, I mean, I start from a very simple model, then I make it a little bit more complicated, and then I look what it can teach us, these simple models can teach us about models which are a little bit more complicated. So I have the ocean, which has a current, and I have the wind, which is blowing above, which has a wind velocity, and there's friction in between. So there's one thing which is important is, of course, the ocean has more mass, so the density of water is much higher, and then the wind. So there is a mass ratio between the ocean and the atmosphere. So the atmosphere above and the ocean below. So I'm looking at a slice of here's the interface, a slice of the atmosphere. So this would be the atmosphere. Then here the ocean, and the ocean layer is it's thinner than the atmosphere. So I have a ratio between this ocean mass, so per unit area, the ocean mass and the atmospheric mass, which is m is chosen in most of my experiments to be equal to 100. So it's just a number. And then there is another very important parameter, which is the friction coefficient. So I use nonlinear friction during all my talk. I will use nonlinear friction. So the friction force per unit area in my models is always given by this friction coefficient, this drag coefficient, times atmospheric density times US. So what is US? US is just the difference between the atmospheric and the oceanic velocities. So I'm looking at the difference in velocities between the ocean and the atmosphere. This is not, I mean, it's not, not everybody does this. In former times when people considered the shear which is applied to the atmosphere, to the ocean from the atmosphere, often in simulations only the atmospheric velocity is considered, and the ocean velocity, which is much smaller, is often neglected. So I don't do this. I have always the shear. And then of course there's friction, so there's depletion of energy, and there's depletion of energy, I need some driving force. So I force the atmosphere. The atmosphere is forced by some type of forcing, and this keeps this is the forcing on the atmosphere, only on the atmosphere, which keeps the system going. And so I'll have 3 slides of motivation why I do what I do. And this is the first slide. This comes out of a work which was done, which I did together with a PhD student of mine, Amy Moulin, where we looked at the same problem just in shallow water. I won't explain why shallow water, but we had a shallow water model for the atmosphere, we had a shallow water model for the ocean, and we had them interact only through friction. So there's no, in all what I say today, there is no heat exchange. I know that heat exchange is very, very important, but I'm not talking about it today. What we had actually is this configuration. So this, what you see, is vorticity. This is on the F-plane, shallow water. This is vorticity in the atmosphere. This is the vorticity in the ocean, and it's biperiodic in the horizontal directions. And then what we had is we had a grid of 4 by 4 cells, and in every cell this forcing was the same, so it's periodic. And so there is the same forcing here, 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 and so there's this periodic picture, and the system is periodic in also in the all the system is periodic. And this is what we saw. So here we have a rather small friction coefficient. CD is 10 to the power of -4. And what you see here, you see the turbulent atmosphere, and you don't really see the forcing in this snapshot. If I would show you an average over a long period, then the forcing, of course, would appears, but you don't see it in an instantaneous snapshot due to the turbulent motion, and the same is somehow true for the atmosphere, and the same is somehow true for the ocean, as you can see here. And so then what we increased the drag coefficient and showed and wanted to see how things changed quantitatively, but finally we saw also that there is a qualitative change.
So how is the forcing actually? I mean, it's a deterministic forcing on your boxes, on your.
Yeah. So the forcing is only on the free surface. So what we actually do is we have a free surface, which is in shallow water, and we project the actual free surface on the forcing pattern. Then we look at the difference, and then we add the forcing pattern so that it is restored, so that the forcing, the mode of the research pattern is restored to the imposed pattern. So this is like if the forcing would be just let me be more precise. If the forcing would just be a sine function, then we kind of do we look at this mode in the solution, and if the amplitude of the mode is too small, we increase it. If it's too high, we decrease it. So this kind of forcing affects only the forcing pattern, the forcing mode, and all the other dynamics is unaffected by this type of forcing. It's actually equivalent. So if people look at flow through a tube, sometimes they impose the through flow, and they keep it constant, and so the transport, and this is the same thing. Just we don't impose the through flow, but we impose the amplitude of this of one mode, which is the forcing mode actually. So that's what we do. This is a nice way to inject energy in just one mode and to leave the other modes unaffected. That they are not directly affected by the forcing. And so we did this also for this higher friction coefficient simulation, and what we saw was something very different, because we saw this picture, and this picture did not evolve in time, so it was frozen. We didn't have any time evolution. So what we have is here we have some spatial variability, but we don't have temporal variability, because if there weren't spatial variability, then the value here would be the same here, here in all of these 16 squares, but that's not what happened. And so for the lower mode, for the lower friction coefficient, we had temporal variability, and for the higher friction coefficient, we actually had only spatial variability and no more temporal variability. And this is true for the atmosphere and the ocean. So they almost don't evolve in time anymore. They're frozen, but they're not frozen in a periodic way. Yeah. Sorry.
So I'm not sure of the equations you're solving. So it's two shallow layers?
Yeah,
so
two shallow water layers.
So
the
interface can be deformed between the ocean and the atmosphere?
Sorry?
Can you deform the interface between the atmosphere and the ocean?
No, it's flat.
Okay. And you have the drag force on both layers? So on one layer and minus the drag force on the other layer?
Yes.
Okay. And you also have small scale dissipation to make it stable, I guess?
Of course, we have some viscosity at the small scale, yes.
Okay, thank you.
Yeah. This actually was a very important remark, because of course the ocean velocity acts on the atmospheric velocity. This is something very important, that we really have a system which acts in both directions.
So I noticed in the, in both plots, some features tend to appear repeatedly. Like for example, in the atmosphere plots, you see some very similar structures at different cells. But like for the ocean, I see some more differences among like the cells. So what causes the difference?
So it's not completely periodic, neither in the atmosphere nor in the ocean. So as you said, there are differences. Where these differences come from, I don't know. I mean, it's not... So then we try to quantify this, and to quantify this, we actually, we separated the variability in spatial variability and temporal variability. So for the spatial variability, we just calculated the average over all these 16 squares, and we also turned it by 90 degrees, calculated the average. So we had an ensemble of 4 times 16, 64, which is of course not independent, all this, but this way we could really calculate an average cell. And then we looked what was the difference between this average cell and the 16 cells which are present here. And then we also looked at the temporal variabilities. That is, we looked over several integrations over a long time, and we looked at the variability in time. And the result is what you see here, is that for the lower friction coefficient, what you actually see is, so this is the total variability. What is white is the temporal variability, and what is black is the spatial variability. And what you see is that for the lower friction coefficients, actually we don't have almost nothing no spatial variability. So if I would show averages for the low friction drag coefficients, then the averages would be completely periodic in space. Whereas for the higher one, spatial variability has almost decreased to zero. Temporal variability has almost decreased to zero, and everything, all the variability is in the spatial part, so it's completely frozen. So this is something which we observed, which happened, and so what we thought about is that this might be question.
Just to be sure, by variability you mean the variance of
The
the
variance,
field?
yes.
Okay, and that why is that units meter to the a second to the -2 if it's a variance of velocity?
It's we looked at it in vorticity.
Ah, vorticity. Okay.
So all the plots I showed were vorticity plots, actually. And so this resembles somehow what is known in condensed matter physics, glass transition. And so to explain this, let me show three slides about the glass transition. So when I was in high school, I was taught that there are three phases to matter: gas, liquid, and solid. And if something is solid, then it has a crystalline or ordered structure, like you see it here. This is taken from the internet, and this is how to explain the three phases of matter. However, if you look at the solids which are around us, most of them do not have this ordered structure, but rather a disordered structure, like a glass. So we have of course glass here, which is solid, but which has also a disordered structure, so it doesn't have a crystalline structure, and it's more like a fluid with a very high viscosity. And so if a substance goes through a glass transition, what happens is just that its viscosity increases, and increases dramatically. So classical values are many orders of magnitude, so you have often 10 or 14 orders of magnitude. So the glass here is probably well, if you would wait for thousands of years, it probably flow down with time, but it takes a very, very long time. It has this solid aspect, but it has the order of a glass. So I think, I'm not sure, of course, that the same thing happened in this air-sea interaction, and this is what I'm wanting to explore. So glass is the most interesting state when it comes to matter, but also when it comes to men. And so let me come back to this painting. And when I hung up this painting in my office, I put it around this way, but I could have also put it around. I was hesitating, maybe should put it around the other way. And so after all, doesn't seem to be too much difference between the atmosphere in the oceans and the view of this artist. And so this made me think about an analogy. This is the analogy of Brownian motion. So in Brownian motion, you have particles, so big particles, which are, small particles, but big with respect to the surrounding molecules. And these big particles move around. I don't know if you have, I think everybody has heard about Brownian motion. So I think it was in 1826 that this botanist, Mr. Brown, he did some experiments. He had some pollen, he put it into water, and he looked under his microscope, and he saw that this pollen was moving around in a kind of a random way. And then he thought, well, this is because the pollen is alive. He put some stone, he took some stone, he made some powder out of stone, and did the same experiment. And still this powder was moving around, and was what is now now called performing Brownian motion. And so this is due to the atoms or molecules around this particle, which bang into this particle and drive it and make it go around. And if you look for a longer time, then it does this movements like they are given here. So it moves in different direction, kind of, you have impression that it moves randomly in different directions. So my idea was that the ocean and the atmosphere is a little bit the same thing, because you have the ocean, which has a lot of mass. Above you have the atmosphere, which has a low mass. The atmosphere is moving very fast in all the directions, kind of a little bit randomly. It's turbulent, and then it also pushes the ocean in different directions. So it's kind of an analogy to Brownian motion. And so I wanted to investigate if this analogy can be pushed even further. I don't know if people have talked about this or have thought about this analogy. I haven't heard about it. So for Brownian motion, it was Albert Einstein who solved the problem in 1905. So he published many very important papers. His most important, he published very important papers in 1905. And one of his papers was on Brownian motion. And at that time, it wasn't even sure that molecules or atoms existed. So kind of this work was also proof about the existence of molecules and atoms. And so Einstein had the idea that actually the movement of this Brownian particle is governed by two processes. The first process is the Stokes force. So it's the force that is acting on any sphere which is moving slowly in a fluid. So if you have a viscous fluid, if a sphere is moving in a viscous fluid, there is, and it's if it's laminar, then you can calculate the force. It's Mr. Stokes who did it, and the inverse friction time is given by the parameter gamma, which is here. It depends on the radius and the dynamic viscosity, which are given here. So this is something which comes out of the macroscopic world. And then there's another thing which comes out of the microscopic world, which is the bouncing of these molecules, which is random. And the work of Albert Einstein was to find out that if you look at such a particle and you look at its distance, or more precisely at its square distance, how is square distance is evolving, and if you divide this by 2 times the time, then this is a constant d, which is the diffusion constant. So he proved that this is the diffusion constant, which you can potentially observe. And it's also equal to some r, where r is just the power of the kicking of the forcing. You don't really need it here. It's just it makes calculation easier, divided by gamma squared. Then Albert Einstein continued the calculations and found that the square velocity is equal to r over gamma. The averaged square velocity is r over gamma. And he also said, so this is from the microscopic world, and from the microscopic world we also have that the equipartition of energy, so that every particle has the same energy, and so this Brownian particle has the same energy as a molecule, which is the temperature, or K Boltzmann times the temperature, divided, U squared is divided by the mass. And so if you put all this together, and if you observe the diffusion coefficient, this is the gas constant, and then you can here you have the Avogadro's number. So how many particles are in 1 mole? So if you can measure if you can measure the diffusion coefficient and temperature, and if you know the radius, then you can actually obtain Avogadro's number. So these experiments were subsequently done by Jean Perrin, who then calculated Avogadro's number in many different ways, and they were all almost identical. And so Jean Perrin got the Nobel Prize for this work in 1926. Albert Einstein got in 1921, Jean Perrin in 1926. And anybody knows what Jean Perrin did next? He founded the CNRS. So he's the founding president of the CNRS, who's employing me and other colleagues here in the room. And so later on, Langevin put up an equation, which is called the Langevin equation, which is given here. So probably most of you already know what I'm talking about. So if I have to go faster, or don't hesitate, so I can also skip this. But I mean, I need this for the sequel also. But so the Langevin equation is just if you take the acceleration of the Brownian particle, and it's subject to two forces, the Stokes force here, and the kicking by this small molecules. And then if you pose, what I did here is, if you say that, well, U is just dtx, so I introduced x here. If you do just some basic calculation, and you say that the force of the particles, the force kicking on the Brownian particle does not depend on x, on the positions of it's homogeneous, then you can drop this term, and then you get the same result of Albert Einstein in a few lines of calculation. It is done here. And so the problem with this equation was that at that time nobody really knew what F is. So this random noise, this which is delta correlated in time, so which has no correlation from one instant of time to the next. There was no mathematical theory about it. It took another 30 years for this theory to develop. It was done by Ito, and if you do this Ito calculus, then you can just write the solutions very simply. So the velocity of the Brownian particle is just given by the initial velocity times exponential function times an integral over the forcing, because it's just a linear equation. And you can also look at the square velocity given here, and the square velocity is depending on the correlation. The average of the square velocity is depending on the correlation of the force, and this is equal to this 2r, where r is the strength of the forcing, and is delta correlated in time. Yes, please.
Sorry for the slide before this. Is there an intuitive reason to understand why x and f should be uncorrelated? Because that's the main step.
So actually this was already observed apparently by Brown, that when he looked at two particles who were moving around, even if they were a very small distance, they were moving independently. So this particle moving here, Brownian particle moving here, and Brownian particle moving here didn't have any correlation. So and what you have here now is you get an equation again for u squared here, which is equal to which is given by equipartition of energy. And what you see, it connects the forcing and the dissipation. So it connects the microscopic world and the macroscopic world. And this is known as the fluctuation dissipation relation. So at some point we can see that it's not much of a surprise, because the dissipation and the fluctuation, they come from the same origin, from the fluid around. So somehow they should be connected. And establishing a connection between, let's say, the kicking of the system and the dissipation of the system is given by this fluctuation dissipation relation. And for the Brownian particle, it's just done by the equipartition of energy. So we know this, then we know the relation between these two. Okay, so this was the little excursion to Brownian motion. Before I now go on with my model, and this is the same picture that I have shown before, and so now I'd like to show you a film about what's happening. And so I made numerical simulation of this problem, and this is what you see here. So as you can imagine, left side is the atmosphere, right side is the ocean, and the atmosphere is forced again by the same type of forcing. So at every instant of time, the vorticity is projected on a mode, which is the mode k equals 80 here. So you have 80 maxima and minima. They're in this line, and it's kx in this direction, which gives the forcing, which is restored always to its initial value, and only this mode is kept fixed, and the other modes are not touched upon. And what you see is now the atmosphere moving around, and actually the ocean you almost don't see moving. So I have a film which moves a little bit. So the same film, I can make it move a little bit faster. So this was slower. This was already the fast version. So the problem with it is that I had a slow and a fast version, but my small computer here, the fast version goes very slow because the computer is too, or the graphics card is too small. Anyway, when I show the slow and the fast version, on the slow version you only see the atmosphere moving. On the fast version you see the ocean moving, but the atmosphere is very, I mean, you don't really see movement because everything goes so quickly. So this is the problem in air-sea interaction, that you have an atmosphere which moves very fast, and you have an ocean which is moving very slowly. So you have what's called a stiffness problem, and usually this is done by to facilitate the integration. The ocean and the atmosphere are integrated on different resolutions in time and space, and it's not what I do. So I integrate the ocean and the atmosphere at the same grid points with the same resolution in space, same grid points, and also the same temporal evolution and the resolution, and there is an exchange of information at every time step. So I have really a system with two parts, a fast part and a slow part, and they evolve together. And this simulation has a resolution, spatial resolution of 4096 square points. And so let me go back to my presentation. And so here I again have a picture of this of the atmosphere in the ocean. Here I just made a zoom. You just see 1/100th of the domain which I integrated, just to show you that this small eddies which you just saw moving around, they're really resolved, and you see in between them in the atmosphere a lot of filaments. So a lot of filaments, and because the resolution is very high, I resolve all this dynamics. The dynamics in the ocean looks also with large eddies and even more, seems to be even more filaments in the ocean. So my question is, I wanted to analyze it a little bit more quantitatively, and to this end I do the same thing what we did in Brownian motion, or what it was done in Brownian motion. I looked at the square velocity. If you look at the square velocity in the atmosphere, you see the zigzag motion here, and this is the best fit of a regression line. I did the same thing for the ocean. Ocean, you actually don't see much zigzagging because it's hidden behind the best fit line. So the ocean is evolving almost on a straight line. And I also looked at the correlation of the atmospheric and the ocean velocities, which is this red line, and the best fit is this red line. And if you look at it, it seems that they're both kind of parallel, right? I mean, they're not very far from parallel. So how can we understand this? To understand this, well, I started with the most easiest model you can imagine, which is this here. So now I'm going to talk about local models, so zero-dimensional models. So I'm neglecting the horizontal exchange of momentum, and now everything is 0D. So I have one variable for the ocean, I have one variable for the atmosphere, and they interact, and the ocean velocity is UO, and the atmospheric velocity is UA, and I have the acceleration of UO is given by stability parameter S times this. So here, for a short moment, I do not have a quadratic drag. I have linear drag now. I'll come to quadratic drag later. And if you look at this equation, it looks like, I mean, it is a Langevin equation. You have the atmosphere here, which is moving very fast. And you have the ocean here, which actually dissipates. And if you multiply this equation by UO, what you get is UO dt. UO is equal to minus S UO squared minus UA UO. And this is actually 1/2 UO squared. And so the energy input, the energy increase in the ocean, is a function of the difference between UO squared and the correlation between the atmospheric velocity and the oceanic velocity in this very simple model. And so it's a Langevin equation here, where here you have the systematic drag, and here you have the agitation by the atmosphere. So it's the same thing. However, this model is not good. It doesn't work because it will go to a stationary state. And in my simulations, I didn't find a stationary state, but it had this linear increase of all the square quantities. So I had to go a little bit further, make the model a little bit more complex. And what I did is I just integrated, added a variable for the atmospheric, a dynamic variable for the atmospheric velocity, which is given here. So now I have a forcing which is applied to the atmosphere, which evolves and which then acts on the ocean. And if you look at this equation, you again have this Langevin equation, which is applied to the ocean, but you have a different equation for the atmosphere. So the atmosphere itself, which appears here, is also is subject to this friction, and you have a forcing which is applied here too. So it's a little bit more complicated, but not much, because it's still linear equations. And actually what you can do is you can have a shear mode. So US is just this shear mode here, and you can have a total inertia, which is UA plus m times UO, where m is this 100, because the ocean has a mass which is 100 times larger than the atmosphere. And then I have another variable which I haven't written. So m is equal to, capital M is just m plus 1. So it's actually the total mass, the mass of the ocean, which is 100, plus the mass of the atmosphere, which is equal to 1. And so then you have, if you write down this equations, then it becomes very easy, because actually you have a Langevin equation for the shear mode, and you have a random walk for the total inertia mode. So you have the two modes which are completely uncoupled, and one is just the total inertia, and one is just the shear mode. And of course, these are linear equations. You can solve for US ut, and then you just put this into the equation. You inverse this, and then you put this for UA and UO, and what you get is just these integrals, which are just a linear equation integrals, and this is what you get from from this. And if you look at the square quantities, you just do the calculation. You look at the square quantities, and then you look at averages. So the averages of the unsquared quantities are 0. I mean, the forcing is 0, so it's just everything is 0. However, the square quantities are not 0. And if you do the calculations, you just find what's given here. So you have a linear growth in the ocean, in the atmosphere, the ocean, and the correlation between the ocean and the atmosphere. You have this 2t here, which comes from the random walk. So the random walk is like the second order moment is increasing linearly in time, and then you have other terms. And so if you look for a larger time, so if you forget about the initial part, then all the exponentials here are 0. And if you look at differences of these variables, so UA minus UO squared, or UA squared minus UO squared, or UO minus UO squared, then this linear term drops out, because it's the same in all this. It's always 2t, and you get this just the results. I mean, just the calculations for. Okay, very good. So S is the friction coefficient. M is 101. So it's just the mass of the ocean per unit area, as compared to the mass of the atmosphere, which is 1. So it's this is 100, so it's 101, and R is just the strength of the forcing. So how strong I'm kicking the system. Yes. Yes. So Hasselmann started to introduce. I think it's him who started to introduce this method into climate science, but he looked only at heat flux. So he was on heat flux. I think, and he didn't do these calculations, I guess. He did Fokker-Planck equations, but he didn't do the statistic differential equations. And it's somehow the same, and I think the same things can actually be, I haven't done it, but the same things can be done on heat flux. I mean, I think it should be kind of identical, because the heat capacity of the ocean is much larger than the heat capacity of the atmosphere, and should be a little bit the same things happening. So Hasselmann did this, and Franklin Newell and Hasselmann in the 70s, I guess, somewhere around this dates, did similar things. Yes. So next slide. Yeah. No Coriolis force. Oh yeah, I should have said this. There is, for the moment, there is no Coriolis force.
Okay, but in the previous slides, in your previous work, you included Coriolis force in your.
So in the work in the past, I included Coriolis force, and the Coriolis force, I think, is very important for the glass transition, because it introduces me two scales, because you have a Rossby radius of deformation for the atmosphere and the ocean. So you have two characteristic scales in the system, and this is often thought in condensed matter. It's put forward that this is very important for a glass transition, that you have two types of length scales, or two types of molecules which interact, which are different but not too different. And so here, for the moment, I don't have it, but the next step is very important to include, to do the same things on the F-plane. But for the moment, it's not on the F-plane. It's two-dimensional turbulence.
Okay.
But I mean, technically, changing the code into a quasi-geostrophic code is something which is done in 2 hours. I mean, it's not. There's no technical problem with it.
Okay. And also, previously, if you included Coriolis force, the deformation radius between atmosphere and ocean is very big. So you resolve both of the deformation radiuses.
Yeah, so that's why in the previous I had 2,000 grid points
so
also. So I resolved the 20 kilometers of the ocean and the 200 kilometers of the atmosphere.
So the computation is quite expensive previously.
It was an expensive calculation, and this is why I stopped using shallow water, because with shallow water it was too expensive. I couldn't push it further, and this is why now I do two-dimensional turbulence and later on quasi-geostrophic, because it's much cheaper numerically to integrate these equations. That's a very good question. Yeah. Thank you. Okay, so if you now write this equation, this which is written on the blackboard here, if you write it again here, then you see that for long times you have on the left side r over m squared, and then on the this term here is what's given here. So this is the correlation of the atmospheric velocity and the ocean velocity, and the autocorrelation of the ocean velocity is this. And this is kind of the equivalent to the fluctuation dissipation relation, which is given in which was calculated for the Brownian motion. Here I calculated it, or I showed it, because it's not really a calculation, because it just made this is equal to this, but I mean it's trivial, it's tautological, but it says how the two terms or the three terms combine to each other, and it really works out that you have this this relation between the increase of the variance of the ocean square velocity and the correlation between the atmospheric and the oceanic velocity and the oceanic velocity squared. So this is kind of the fluctuation dissipation relation. And then, well, this was the linear model, but friction is not linear at the surface or between the ocean and the atmosphere. So at one point I went to the quadratic model. So the quadratic model is given here. So it's still zero dimensional. I don't have anything, it's just zero dimensional. So UA, but now we have vectors. Before I just wrote scalars, because in the linear model what happened in the x direction is independent from what happened in the y direction. This is no longer the case if you have quadratic model, because now the u component depends also on the v component, the v component depends on the u component. So you have to use vector notation, but the rest is the same. And you have the new thing is, of course, that you have this absolute value of the shear velocity, as is already written on the blackboard, but you can still separate in a shear mode and a total mode. And then what I wanted to do is I wanted to see if I can reduce this a little bit more complex model on the simpler model to the simpler model, which is the linear model, by introducing a eddy viscosity. So the eddy viscosity can be calculated here explicitly. It's just u squared to the power of 3/2 divided by the average of u squared to the power of 3/2 and times this value, and you can give an analytic formula which is only depending on nu, where nu is given by this here. So this is normalized 3.5 moment of the square velocity. And you can do the calculation, and if u and v, the two components, were Gaussian, then this would be just 3 to the square root of pi over 4, so something like 1.32. But in fact, I managed to calculate, I'll talk about it, I'll calculate, it's not difficult actually, so I found out, to calculate the true value of nu, which is just given here, where gamma is the gamma function. So it's the gamma function of 2/3 divided by the gamma function of 4/3 and 2/3 of this. It's 1 point, so the true value is 1.25 something, and this is 1.3, the Gaussian value, so it's not too different, but it's different. And what you see here in this plot for the zero-dimensional model, you see the integration you see the analytic solution for the linear model, which is the dotted line here. So here you see a difference between the dotted line and the other lines. Then the symbols here, the symbols give the result of the numerical integration of the stochastic differential equation, the linear stochastic differential equation. And the full line give the integration of the quadratic stochastic differential equation. And they both agree almost perfectly. So in black would be the UA squared, red would be UA UO, and green would be UO squared. And this is averaged over, I know this is averaged over many realizations, so this should be omega here. The A's should be omegas. It's averaged over many realizations. There's just a little difference in the beginning, in the build-up, but this is of course because this value here is only calculated for the stationary state. For the spin-up, this values, I mean, it's different. I didn't do the calculation for the spin-up, just for the stationary state. And so things seem to agree. There, of course, it's one-dimensional, zero-dimensional models, so they can be integrated with very large ensembles. Ensemble size is always over 1 million, and so this is why we disagree very well. So I just wanted to make a small parenthesis in 2 minutes left or so, how I calculated this value. Well, to calculate this value, actually, if you have the stochastic problems, you can have two approaches to solve them. One is the stochastic differential equations, which I performed. It's like you start with a particle, and for every noise, realization of a noise, you do the integration, and then after some time you arrive here. You do this for many particles. Here it's 5. I've done it for many millions. And then you can calculate, you can make the statistics, you can calculate the averages or the moments, or you can also reconstruct the PDF. This is kind of a Lagrangian approach. One could say this is a Lagrangian approach because you follow every particle in this integration. You can also use, and this is actually more similar to what Albert Einstein did, you can use the Fokker-Planck equation. So in the Fokker-Planck equation, it's different because you try to write down an equation for the PDF, the probability density function. You write down a partial differential equation, and then you see how it evolves. So how this PDF, this PDF here, moves and how it spreads. This is given by this Fokker-Planck equation. It's kind of an Eulerian approach. So, I mean, is everybody familiar with this, or you want me to explain in 2 minutes? Maybe I explain it, or yeah. So if you have if you for example if you have particles which are moving around, and you want to know how many particles are in a square like this, then you can just look at all the particles and or have many particles, integrate them, and then some are moving out, some are moving in, and then at one point in time you stop and you count how many particles are there. So this would be kind of a Lagrangian approach because you follow the particles how they are moving. But you can also write an equation, or try to find an equation. What is at a certain time, what is the probability of a particle from this here to jump in here, from here to jump in here, and from here to jump out? And so this would be the Eulerian approach, the Fokker-Planck equation approach, where you just write down equations how these evolve. So how is the probability of a particle jumping in or jumping out, and then you get this approach. So you have these two approaches, and for my simple models, then what you have is you can write down the stochastic differential equations, you can write down the Fokker-Planck equations, and here I compare the two, so it gives us, this is a comparison of, and they all fall on the same line because of course my ensemble sizes are so big. And I could also do this for the nonlinear model, where you have this Fokker-Planck equation is given here, and you can solve it, and if you solve it you find out that this is this where E here is now U squared plus V squared, and so it's just a exponential to the power of minus beta to the power of E to the power of 3/2, And then there's a normalization factor which includes the gamma function. So we have these two approaches, and I just wanted to show this because the red line is the Fokker-Planck solution, and the other wiggly lines are actually the integration. So there's perfect agreement for that. And so this is almost my last slide, because I go back to comparing. I mean, now I go back after having spent some time in zero-dimensional space. I go back to two-dimensional space. This is the picture you all have already seen, where you have the correlation UO and the correlation, autocorrelation of UO. And what you see is you can take the gradient out of this. You can calculate the UA, the UO, and the UO squared. And you can use this. So here I used the linear Fokker-Planck equation, and also the linear, the equation for the stochastic differential equations. And I can obtain then, by just looking at all these correlations, I try to estimate the friction, the eddy friction coefficient, and of course I know it. No, the friction coefficient, not eddy, but just the friction coefficient, and I know it, and it's close to the observed value. Yes, please.
Excuse me, could you remind us what beta was in the slide before this?
It's just a constant.
It's just an arbitrary
It's just a constant which is evolving in time for the total mode, because it's a diffusive process, and for the shear mode, it converges to a value, to a constant value.
So this formula that you showed, beta to the 2/3 exponential and so forth, that was the probability distribution, or?
This is the probability distribution for E, for this quantity, for the energy. I mean,
and that you get by solving the stationary
Oh, you just have to find the stationary solution. You just have to find the solution. You put this 0 and you find the solution of this, and so then you have it. Yeah. It's actually not how it happens. How it happens is you do the experiments. You find that it gives a certain law, and then you try to fit, and then you take your fit, you put it in the equation, and it works. Voila. Okay. So the method works very well in estimating or finding the surface friction, and so it can be applied to some extent to the two-dimensional simulations, and this is where I'm about for the moment. I mean, I have other results, of course, also about the estimation of m and the other values in the problem. And to finish, I just conclusions, make few comments. So the first thing is that the ocean subject to atmospheric forcing obeys a fluctuation dissipation relation, which I have written down for this zero-dimensional models. The local models, linear and quadratic, can be solved analytically. So you have analytic solutions of them. Some results from the local models can be transposed to the fully two-dimensional turbulent models. What I wanted to say is it's just the beginning. And then I have two kind of comments. The one is that it's larger than what I'm presenting now, but I mean, it's just maybe for discussion, that today the dissipation, the small-scale structures which increase the dissipation of the system are always included. The dissipative effect of the small-scale structures is included in the atmosphere, ocean, and climate models, but not the fluctuations. But we have fluctuation dissipation relations at all levels in the dynamics. So if you have kind of a Laplace operator to take out the energy, we should also have something which kicks a little bit the system. And for this, of course, you have to write down you have to find the fluctuation dissipation relation. So that both have the nice the good magnitude, so they have that they correspond to each other. And I recently heard that some people who do weather forecasts, they say that too often weather forecasts work better if you do the calculations in single precision rather than double precision. And I think this is a manifestation of the dissipation fluctuation relation, because if you have single precisions and you include some kind of noise, which also kicks the system, and so you have dissipation and fluctuations, but then I think it should be done more precisely, more qualitatively in developing the fluctuation dissipation relations between the two. And then I consider a truly non-equilibrium process. So it's a process which is evolving, so I cannot continue my experiment forever because energy increases. But I think this is important today, that we go to this really non-equilibrium process, not only spin up and spin down, because I mean, we have a certain forcing, the system spins up, but before it reaches equilibrium, I think the forcing, the weather system, or what forces it, has already disappeared, has already changed. So I think this truly non-equilibrium processes are very, very important and should be also considered, because forcing functions also vary in time, and often the adjustment to the forcing, the spin up, is longer than the presence of the forcing. So this is the end of my talk, and I'll be very happy to take your comments, questions.
So can you hope to also have in observation a kind of signature of this relation?
I hope, yes. Probably it's, I'm not at all a specialist of the genesis of cyclones and anticyclones, but I've heard or I've read that in the initial phase, the motion of the ocean could be important in this case, so that if you have an ocean eddy, it might attract an eddy above, an atmospheric eddy. A cyclone, an ocean cyclone, can attract an atmospheric cyclone, have a condition which favors atmospheric cyclones, not only by thermal exchange but also by exchange of momentum, and this might be interesting to consider. But I mean, I haven't gone so far.
So in general, when you have systems with two very different time scale, when you look at the effect of the fast system on the slow one, so you get at leading order an average effect, and then you get at next order a white noise, which amplitude is given by a Kubo formula. So it's basically roughly the variance multiplied by the correlation time that gives you the value of diffusion coefficient in front of it. So I wonder how what you discuss is different from this.
I don't know.
And so what happens very often is that the average is way larger. So for instance, for the real atmosphere acting on the ocean, you have the average wind.
Sorry, you have?
You have the average wind, and then you have the fluctuation.
Yeah.
So one would like to compare the typical effect of the average compared to the effect of the fluctuation, for instance, from the point of view of energy or...
So in my case, for the moment, I do not have an average wind. I mean, the average wind is 0. I don't know if how this applies then what you say.
So I'm not sure to have understood why the two couple systems don't have at all the same time scale for their evolution, because if we assume that there is a very rapid excitation at the surface of the ocean, so even if it's very small, you could have so a small amplitude, small scale forcing, which will end up with the inverse cascade in large scale motion at the same speed. So I don't get why there is this discrepancy in time scale.
So in the linear models, it's clear because I mean you have I mean the mass of the ocean is just so much bigger, and so if you just look at this equation, so this is kind of the inverse of a correlation time, and then you have a factor of 100, right? So it is very different. So locally, it's clear that it's different. Afterwards, there's the problem of the cascade, the energy and the entropy cascade. And something which I have not said is that this actually, why do I need, in the two-dimensional model, why do I need 4,000 times 4,000? It's because if this, for this to be true, I do not have, I'm not allowed to have dissipation here, another kind of dissipation of energy. And if the ocean model doesn't have enough resolution, then there is too much energy dissipated. But in two-dimensional turbulence, and also in quasi-geostrophic turbulence, you have an inverse cascade of energy. And so there is no dissipation of energy if you have infinite resolution. And this is why I use this very, very high resolution model. So I did it before with half the resolution in each direction, and it didn't work very well. So you really need very high resolution models, not to have another term, an important term here, which dissipates. So, but probably doesn't answer your question, what I just said. Yeah, okay.
Okay, thanks again, Archim.
Okay, thank you.